Hi, and welcome to Lesson 4A here in our reactions unit. Here we're going to be talking about advanced reaction stoichiometry. Remember, the letter after the number in our lesson scheme means that this is an honors-only lesson. We're going to use this sandwich example to start, which is going to get at a point that I want to make. So if I wanted to make a sandwich, kind of a plain sandwich, but I might want to use 2 slices of bread and 1 slice of cheese. Make sense? So we have a recipe for a sandwich. 2 slices of bread plus 1 slice of cheese. What would happen if I had 28 slices of bread and 11 slices of cheese? How many sandwiches could I make? Do you think you know? The answer is 11. I can make 11 sandwiches because I only have 11 slices of cheese. Even though I have enough bread to make 14 sandwiches, I can't make them all because I run out of cheese first. The cheese is limiting what I can do here. That's the basic point of what we're about to discuss. Most times in the real world, chemical reactions don't occur in perfect molar ratios. There's always going to be more of one substance that is needed and less of the other substance. That substance that will run out first is called the limiting reactant. In our sandwich example, it was the cheese. In our chemical examples, it's going to be different chemicals in the equations. At the Regents level, the chemistry mole ratio problems just always deal with perfect ratios. But you are an honor student, and so you should be able to deal with limiting reagents. For the one thing, it's a little bit more complicated, but for the other, it's basically impossible to have these perfect situations in real life. So you really do have to have a handle on how to deal with limiting reactants in general chemistry if you actually really ever want to do actual chemistry. Real reactions only proceed until that limiting reactant is totally consumed. That's the definition of the term. Does this make sense? If not, here's the bottom line. The amount of a product produced in a chemical reaction depends upon the limiting reactant. It does not depend so much upon any other reactant because we have more of that other reactant than we need to use before all of our limiting reactant gets used up. Here's an example: hydrogen gas and chlorine gas, the chemical analog of our sandwich. So hydrogen gas combines with chlorine gas to make 2 hydrogen chloride molecules. If you look before the reaction, we have 4 molecules of chlorine, which are the big green atoms, and we have 6 molecules of hydrogen, which are the little white atoms. But after the reaction, we still have 2 hydrogens remaining. That's because chlorine is our limiting reactant. We can only react those 8 chlorine atoms with 8 out of our total 12 hydrogen atoms. After that's done, there's just no more chlorine to react with the hydrogen. This is what a limiting reactant is. You're going to need to be able to solve limiting reactant problems. It's not all that different from what we did in our equation stoichiometry, but there is one small change. The first thing you're going to need to do is convert all of the reactant quantities to moles, and then you're going to use the mole ratio for a selected reactant to figure out if it's limiting. Here's how you do that. Look at the mole ratio for a particular reactant compared to the other one, and figure out if you have more than you need to use all of the other reactant. If you don't, then the one that you've chosen is the limiting reactant. If you do, then the one that you've chosen is not the limiting reactant. It's what we'd say to be in excess, and the other reactant is the limiting reactant. Once you know that, you use the limiting reactant to determine the total amount of whatever product is going to be produced and answer the question. Let's do this example. It's not in our packet. In the following reaction, 2 CO molecules plus O2 gives you 2 CO2. We're going to react 28.0 grams of CO with 28.0 grams of O2. What's the limiting reactant and how much CO2 should be produced? Pause the video and try it on your own, and then when you're ready, we'll go through it together. So the first thing we need to do is convert all reactant quantities to moles. 28.0 grams of carbon monoxide is equal to 1 mole of carbon monoxide. If you have questions about how I did that, you definitely want to go back to conversions or maybe even our most recent lesson on reaction stoichiometry. 28.0 grams of oxygen is equal to 0.875 moles. So we've got different numbers of moles of each of these substances. Now that that's done, we can move to step 2. Determine if a reactant is limiting. I'm going to choose to look at carbon monoxide. I just always pick the one that's on the left first. So the ratio of carbon monoxide to oxygen is 2 to 1. I have 1 mole of carbon monoxide. If I used up all of that carbon monoxide, how much oxygen would I need? Solving for X, I get 0.5 moles. Do I have 0.5 moles of oxygen gas? The answer is no. I have more than 0.5 moles of oxygen gas. What this means is that I will use up all of the carbon monoxide before I use up all of the oxygen gas. In other words, carbon monoxide is my limiting reactant. Now I'm going to use the limiting reactant to answer the second question. How much carbon dioxide should be produced? Let's look at the mole ratio between carbon monoxide and carbon dioxide. Remember, I only need to worry about my limiting reactant mole ratio. I don't need to worry about the oxygen because I have more of it than I'll use before I use up all of my carbon monoxide. The ratio is 2 to 2, also known as 1 to 1. If I have 1 mole of carbon monoxide, I should expect 1 mole of CO2 to be produced. Of course, from that point, I could convert that 1 mole of CO2 to grams, numbers of particles, liters of a gas at STP. I can do all of those things if I want to. But for right now, we're just going to leave this here and move on. Does this make sense? If it doesn't, take a moment and write down any questions that you have before we talk about the other kind of advanced calculation we can do. Our other advanced calculation is percent yield. This equation is not in your reference tables. Real reactions very rarely produce as much of a product as they are theoretically supposed to produce. That's what we call the theoretical yield, the maximum that we expect. Percent yield is a way to determine how efficient a particular reaction is. The formula for percent yield is the actual yield of the reaction divided by the theoretical yield times 100. It's a bit like percent mass or percent anything else, except here we're just talking about the amount produced in a chemical reaction. Let's try this percent yield question to get a handle on what we're doing. So here's our earlier reaction from before. If we produce 33.0 grams of CO2, what's the percent yield for the reaction? Theoretically, we should produce 1 mole of CO2. 1 mole of CO2 has a mass of 44.0 grams, but we didn't produce that much. We only produced 33.0 grams. So our percent yield is going to be equal to our actual yield, 33.0, divided by our theoretical yield, 44.0, times 100. Our percent yield for this reaction is 75%, which is actually, in the grand scheme of things, a pretty good percent yield, much better than what we'd see in a lot of the conventional commercial chemistry that's used throughout the world. Does this make sense? If it doesn't, take a moment and write down any questions that you have before we wrap up. Thanks so much for watching our discussion of advanced formula stoichiometry. Make sure you can do the following things here at the end. Make sure that you can determine the limiting and excess reactants in formula stoichiometry problems. If I give you the information in the equation, you should be able to figure out who's limiting and who is in excess. Also make sure that you can use limiting reactants to determine the theoretical yield for a particular reaction. And finally, make sure that you can calculate the percent yield for a particular reaction if you're given the data that you need. If you can do all these things, you're doing great. If not, that's okay too. Take a moment, write down any questions that you have. You can always leave them for me below the video, and you can always get in touch with me. Thanks again for watching. I really appreciate it. Have a great day.